In the summer of 2022, the James Webb Space Telescope released its very first deep field image, a single patch of sky, smaller than a grain of sand held at arm's length, packed with thousands of galaxies stretching back toward the beginning of time. Picture that image the way the public first saw it, a black background scattered with swirling spirals, smudged ellipticals, and faint arcs of gravitationally warped light, each one a galaxy, some of them older than our own sun. Astronomers expected surprises. What they didn't expect was for some of the earliest, faintest points of light in that image to quietly contradict the standard model of how the universe itself is supposed to have formed. For nearly 3 years, teams of scientists have been trying to explain away a population of strange, compact, blood-red objects scattered through Webb's deepest images, objects so small the most powerful space telescope ever built still can't resolve their shape, and so unexpectedly massive that some researchers openly admit they didn't want them to be real. This is the story of the little red dots, and why finding them might be one of the most quietly unsettling discoveries in modern astronomy. To understand why these objects cause so much trouble, you first need to understand what astronomers expected to find instead. The standard model of cosmology, the mathematical framework built up over decades to describe how the universe evolved from the Big Bang to the galaxies we see today, makes a fairly specific prediction about the early universe. Right after the Big Bang, matter was spread almost perfectly smoothly through space with only the faintest ripples of unevenness. Under gravity, those ripples slowly grew, pulling gas together into the first small clumps of stars, which then merged over hundreds of millions and eventually billions of years into progressively larger galaxies. Picture it like a city growing from a scattering of single houses into a sprawling metropolis, a process that takes real time to unfold, brick by brick, block by block. According to that model, galaxies in the first few hundred million years after the Big Bang should have been small, faint, and still under construction, nothing close to the massive, mature-looking systems we see nearby today. That's not entirely what Webb found. Almost immediately after its first images came back, astronomers noticed there were more large, apparently mature-looking galaxies in the infant universe than anyone had predicted, enough of a mismatch that some researchers began quietly describing it as a genuine problem for the standard model rather than a minor surprise. And tucked among those unexpectedly massive galaxies was something even stranger, small, unresolved, intensely red points of light that didn't behave. Like anything cataloged before, Webb's cameras, sensitive enough to make out the structure of galaxies billions of light years away, simply couldn't resolve these objects into any recognizable shape. Whatever they were, they had to be smaller than roughly 2% of the diameter of the Milky Way, packed into an almost point-like source, and yet still bright enough in Webb's data to rival galaxies many times their apparent size. Researchers nicknamed them little red dots, a plain, almost dismissive name for something that turned out to be anything but simple. The first instinct among astronomers was to assume these were simply very old, very red galaxies, since aging starlight does tend to redden over cosmic time. But that explanation ran into an immediate wall. To produce that much light from an object that compact using only ordinary stars, you would need a packing density of stars so extreme it strains what's physically plausible. Stars crammed shoulder to shoulder across the whole volume of the object, in a way nothing in the nearby universe resembles. Caitlin Casey, an astronomer at the University of Texas at Austin who has studied these objects closely, has described the situation plainly. Figuring out why they were so spatially compact was, in her words, a genuine mystery. If it wasn't an impossibly dense cluster of stars producing that light, something else had to be. It's worth pausing to explain how astronomers can even claim to know these objects are that old and that far away, since the whole story hinges on that measurement being trustworthy. As the universe expands, galaxies rush apart from each other, and the light traveling between them gets stretched out, shifted toward longer, redder wavelengths, an effect astronomers call redshift. The more a galaxy's light has been stretched, the further it has traveled, and the further back in cosmic time astronomers are actually looking, since that light left its source long before it ever reached Webb's mirror. By carefully measuring exactly how far a distant object's light has shifted, astronomers can calculate not just how far away it is, but how old the universe itself was at the moment that light was emitted. That's the same technique that places Canucks LRD Z8.6's light as having left its source just 570 million years after the Big Bang, and it's a well-established, heavily cross-checked measurement, not a rough guess. The strangeness of these objects isn't coming from uncertainty about when they existed. It's coming from what they were already doing at that moment. That something else turned out to be almost as unsettling as the alternative it replaced. The leading explanation now favored by most researchers studying little red dots is that they aren't ordinary galaxies at all, but galaxies with an actively feeding, supermassive black hole blazing at their center, a compact engine capable of outshining the combined light of billions of ordinary stars from a region barely larger than a solar system. That explanation solves the size problem elegantly. It also opens up a new one, because it means Webb has been quietly cataloging an entire population of supermassive black holes that, by every existing model of galaxy formation, shouldn't have had time to grow that large yet. Here's why that timing problem is so serious. Nearly every galaxy in the nearby universe, including our own Milky Way, hosts a supermassive black hole at its center. And decades of observation have revealed a strikingly consistent relationship between a galaxy's total mass and the mass of the black hole sitting inside it. Bigger galaxies reliably host bigger black holes in a ratio that holds remarkably steady across an enormous range of galaxy sizes, suggesting the two grow up together, feeding off each other's development over billions of years. The black holes powering little red dots don't follow that rule. Kevin Finkelstein, an astronomer who has worked extensively with Webb's early universe survey data, has been candid about what the numbers actually show. If the black hole masses being measured are accurate, they come out overmassive compared to the galaxies hosting them, sometimes by 1 to 2 orders of magnitude, beyond what the established relationship would predict. In plain terms, that means some of these early black holes appear tens to over 100 times heavier relative to their host galaxy than the ratio every nearby galaxy in the universe seems to respect. That kind of discrepancy doesn't have an easy fix, because it runs headfirst into basic physics. Black holes can only consume matter so quickly. Picture a black hole feeding the way a drain handles water. Pour water in gently and it disappears smoothly, but pour too much in at once and the water backs up, splashing outward instead of draining. There's a well-established theoretical ceiling called the Eddington limit on how fast a black hole can feed before the radiation pressure from all that infalling, superheated material starts pushing new material away faster than gravity can pull it in. The black hole equivalent of a drain that starts overflowing under too much pressure. Starting from an ordinary stellar mass black hole, the kind left behind when a single massive star collapses, and growing it up to the size these little red dots seem to require, all within the first few 100 million years after the Big Bang, using only that. Natural feeding limit simply doesn't add up on paper. Run the math forward from a typical stellar mass starting point, feeding at the maximum sustainable rate the whole way, and you still fall dramatically short of the masses Webb is actually recording this early. Something about the earliest black holes in the universe appears to be fundamentally different from what standard models predicted, either in how fast they can feed or in how big they were allowed to start out in the first place. This is exactly the kind of result nobody in the field was rooting for, and it's worth being honest about why. Cosmology isn't just a loose set of educated guesses. The standard model has been tested and refined against an enormous range of independent evidence, from the leftover glow of the Big Bang itself, a faint microwave afterglow filling the entire sky that's been mapped in exquisite detail by multiple dedicated satellites, to the large-scale structure of galaxies, stretching across the observable universe in vast cosmic webs of filaments and voids, and it has held up remarkably well for decades. A result that seems to contradict one of its core assumptions about how quickly structure can form isn't the kind of headline scientists chase for excitement. It's the kind of result that makes them go back and recheck their own instruments, their own calibrations, their own math, hoping to find the mistake was theirs rather than the model's. Multiple independent teams have now done exactly that kind of rechecking, using different surveys, different telescopes, and different analysis pipelines. The little red dots and their oversized black holes have, so far, refused to go away. One especially striking example arrived through a survey called CANX, when researchers confirmed an actively growing supermassive black hole inside a galaxy dating to just 570 million years after the Big Bang, catalogued as CANX LRD Z8 5. 170 million years sounds like an enormous span of time in ordinary conversation, but set against a nearly 14 billion-year-old universe, it's an almost impossibly early moment for a black hole of that scale to already be up and running, actively pulling in surrounding gas and shining brightly enough for an instrument light years away to notice it at all. Researchers studying the object have described it as connecting the dots between these strange early black holes and the more familiar, brilliantly glowing quasars. Astronomers have studied for decades at slightly later points in cosmic history, suggesting little red dots may represent an early, formative stage that black holes pass through on their way to becoming the monsters we see powering galaxies today. So if standard growth from an ordinary stellar remnant can't explain the timeline, what can? Researchers have converged on a small set of competing ideas, none of which was seriously considered mainstream before Webb forced the issue. The leading candidate is something called heavy seed formation, the idea that some early black holes didn't start out small at all, Instead of forming from the collapse of a single dying star, they may have formed directly from the sudden catastrophic collapse of an enormous, pristine cloud of primordial gas, skipping the usual intermediate step of becoming a star first, and instead collapsing straight into a black hole, already tens of thousands or even millions of times the mass of our sun. Starting that far ahead in the race would give a black hole billions of years worth of head start compressed into the universe's earliest few 100 million years, potentially explaining how something like Canucks LRD Z8.6 could already be feeding so aggressively so soon. A second, even stranger possibility has emerged from researchers studying the little red dots most closely. That at least some of them aren't simply black holes embedded inside small galaxies, but an entirely new category of object. Some scientists have started calling black hole stars a colossal ball of extremely hot, dense gas larger than our entire solar system with a black hole buried. At its core, acting as the engine instead of nuclear fusion. Picture something like a star turned inside out. Instead of a fusion furnace at the center pushing light outward against gravity the way our own sun does, imagine a black hole at the center instead, tearing and falling gas apart and superheating it so violently that the entire surrounding envelope glows, effectively wearing the black hole's feeding frenzy like a luminous skin many times larger than the black hole itself. Jenny Green, an astrophysicist at Princeton University who has worked on characterizing these objects, has said the picture is finally starting to come into focus after years of confusion, describing the emerging consensus as genuinely exciting rather than merely puzzling. If that interpretation holds up, it would represent a genuinely new class of astrophysical object, something theorists had modeled as a mathematical curiosity for years, without ever expecting to actually catch one glowing in real observational data. There's also a third, more primordial possibility still being actively explored, that some of these black holes didn't form from collapsing gas or dying stars at all, but trace back to so-called primordial black holes, hypothetical objects that some models predict could have formed directly from density fluctuations in the fabric of the universe itself within the first fraction of a second after the Big Bang, long before the first stars or galaxies existed in any form. Under this scenario, small, tightly packed clusters of these primordial black holes could have merged together repeatedly over cosmic time, spiraling into each other and combining their mass again and again in a runaway process, snowballing into the oversized black holes little red dots now appear to host, all without ever needing a single ordinary star to collapse first. It's a genuinely exotic idea, closer to the kind of physics usually reserved for the very earliest instance of the universe rather than galaxy formation, and researchers pursuing it have pointed out that if it's correct, it should leave behind a distinctive signature in gravitational waves, ripples in space-time produced by black hole mergers, potentially even detectable as a faint background hum spread across the entire sky that future gravitational wave observatories could, in principle, actually go looking for, giving scientists a completely independent way to test the idea beyond simply staring at more little red dots through a telescope. It's important to be honest about how unsettled all of this still is, because that honesty is part of what makes the story credible rather than sensational. Not every astronomer agrees that little red dots are even black hole powered in the first place. Some researchers continue to argue that at least a portion of the population could still be explained by extremely dense, dust-obscured pockets of star formation rather than active black holes, since dust can redden and dim light in ways that partly mimic what's being observed, and untangling exactly how much dust is doing the work has become its own active area of research. Other teams have run large-scale simulations suggesting that, given enough additional time to evolve, these overmassive black hole ratios might gradually shrink back towards something closer to normal as their host galaxies keep growing around them, meaning the current mismatch could eventually resolve itself without requiring exotic new physics at all, simply because we happen to be catching these systems at an unusually lopsided early moment in their development. Competing papers on the same population of objects, published within months of each other, have reached genuinely different conclusions about how alarmed the field should actually be. That range of disagreement is, in its own way, the most honest part of this entire story. Little red dots aren't a single, tidy discovery with one confirmed explanation. They're a live, unresolved argument playing out in real time across dozens of research papers, precisely because Webb's data keeps arriving faster than any single model can be tested against it. What almost everyone studying the topic does agree on is narrower but still significant. Something about the population of black holes in the first billion years of cosmic history looks different from what pre-Webb models predicted. Whether that difference eventually gets explained by heavy seeds, black hole stars, primordial mergers, dust effects, or some combination none of these teams have proposed yet. So here's what makes this discovery worth sitting with, beyond the specific numbers and competing models. For most of the history of modern cosmology, The standard picture of how galaxies and black holes grow up together has been treated as one of the more solid, well-tested pillars of the field, built on decades of consistent observations across the nearby universe. Webb didn't set out to challenge that picture. It was simply built to look further back in time and with greater clarity than any instrument before it. And the moment it did, a population of objects nobody had specifically predicted showed up anyway, small, red, impossibly compact, and quietly out of step with what everyone expected to find there. Scientists didn't go looking for something that would complicate their own foundational model. The universe handed it to them regardless, sitting right there in the deepest images ever taken, waiting patiently for someone to notice it didn't fit. That's really the heart of why this story carries the weight it does. It isn't a discovery anyone wanted, the sense of confirming something comfortable or expected. It's a discovery that arrived anyway, forcing careful, methodical scientists to spend years rechecking their own assumptions rather than simply accepting a convenient answer, precisely because the alternative, quietly ignoring an inconvenient result, isn't how good science is supposed to work. There's something almost reassuring buried inside that discomfort, if you look at it from a slightly different angle. A model robust enough to have survived decades of testing didn't crumble the moment one anomaly turned up. Instead, an entire field of trained scientists did exactly what they were supposed to do. They didn't throw out the standard model, and they didn't pretend the little red dots weren't there either. They sat inside the discomfort of an unresolved contradiction for years, testing it from every possible angle, because that discomfort is precisely what real scientific progress is built out of. And as of right now, tonight, hundreds of these little red dots are still sitting in Webb's archived data, some of them barely analyzed, each one a tiny, stubborn red point of light from the first billion years of time itself, quietly waiting to tell us whether our best model of the universe needs a footnote, a revision, or something closer to a rewrite. Somewhere in an observatory control room, new Webb data from an even deeper survey is already being queued up for analysis, and there is a real chance that the object that finally settles this entire argument one way or the other is sitting in that queue right now, already captured, already sent home across millions of miles of empty space, just not yet looked at closely enough for anyone to know what it's about to say,